xn epsilon, ultimately epsilon close to L, yn ultimately epsilon close to M implies that the sum, so I'm telling you that with an error epsilon, the first number is L, and with an error epsilon, the second number is M. So I expect that with an error of 2 epsilon, their sum is L plus M. That's it. That's all that is here. Okay? So xn plus epsilon should be ultimately 2 epsilon close to L plus M. So that's it. Okay? If I know that a number is within an error close to L, and another number is within the same error close to M, then their sum will be close to the sum of L and M with an error which is just the sum of the errors. And then I will play with the fact that my error was arbitrary in all of this. So let's check this. So formally, so the goal is checking that for every epsilon positive, xn plus yn is ultimately epsilon close to L plus n, right? This is equivalent, actually, to say that for every epsilon positive, xn plus yn is ultimately 2 epsilon close to L plus n. So be very careful. It's not true that being epsilon close implies that you are 2 epsilon close, right? But not vice versa. So it's not true that being 2 epsilon close to something implies that you are epsilon close. That's false. Take epsilon equal to 1. Being 2 close to a number doesn't imply that you are 1 close. We all agree on that, right? So the trick is that when you have the definition of limit, there is a for every epsilon, which changes completely the rules of the game. Because if for every epsilon I am 2 epsilon close, well, 2 epsilon is just an arbitrary positive number. It's just me that I have decided to write it in a funny way, as twice epsilon, right? But it doesn't change anything. So check that saying these or saying that about the sequence is the same. Okay, can you check that for me? And, okay, that's an exercise for you, okay? The fact that for every epsilon you are epsilon close to something, ultimately, is equivalent to the fact that for every epsilon you are ultimately 2 epsilon close to that something. Simply because this will be anyway generic positive. One implication is trivial, because if you're epsilon close, you're also 2 epsilon close, that's it. The other implication just requires a little trick. I mean, a bit of thinking, but it's just a formality. Okay, once you have that, in mind, you can do this. So you can say, well, by assumption, for every epsilon positive, there exists some threshold such that xn minus L is less than epsilon for every n greater or equal than an epsilon. And there exists a second threshold, m of epsilon, such that yn minus m is less than epsilon for every n larger than m epsilon. So I've just written down the definition of limit for xn and yn, right? That's what it means. So we do exactly the same trick we did in the previous proof. Okay, then, so set k epsilon to be defined as the maximum between the first threshold and the second threshold. This would be a natural number, all right, with the property that for every epsilon, if n is larger than this k epsilon, then both properties will hold. xn will be epsilon close to L, and yn will be epsilon close to L. us write these conditions. So this is actually equivalent in asserting that 4 inequalities is equal to 0. So the first one is L minus epsilon less than xn less than L plus epsilon. The second one is yn less than n plus epsilon larger than n minus epsilon. Right? I'm just rewriting without using the absolute value my pair of inequalities. So these 2 inequalities for the absolute values actually turn out to be 4 inequalities for these numbers, x and okay. And what does it say? It says that, so if you add them up, this says that xn plus yn is less than L plus n plus 2 epsilon. And it says that xn plus yn is larger than L plus n minus twice epsilon, right? You see, you add up the upper inequalities, you have that xn plus yn is less than L plus n plus epsilon plus epsilon. And you add up the lower bounds, and you have that L plus n minus epsilon is less than the sum. And what does it mean, this thing? It means that xn plus yn minus L plus n is less than 2 epsilon. So, all in all, if I forget about the proof, what I'll say is that for every epsilon, if n is larger than this k epsilon, then this thing, xn plus yn, is 2 epsilon close to L plus n. Which was exactly our goal, right? Showing that this xn plus yn is ultimately 2 epsilon close to L plus n. So this is proof.
So for this proof, we have to show that 2E closed is the same as E closed?
Yeah. Okay.
Or do we have to show the other way around? Like E closed is.
Well, being epsilon close implies 2 epsilon close, because 2 epsilon is always larger
But
than.
it doesn't work the other way, right?
It works the other way too. And it works not at fixed epsilon, that's the point. So it's not true, if you fix a value of epsilon, it's not true that this implies that, right? Because here I'm using the larger error. But if you ask that, so you have to include the for every inside the box, okay? If you know that for every epsilon you are 2 epsilon close, then you can show that for every positive number you are epsilon close. Let me do this for you. Let's say that instead of using epsilon here, I use delta. You agree that if I change a symbol, it's the same property, right? And it's just the symbol I'm using to denote a positive number, okay? Okay, if I do that, it's quite clear that every delta positive can be written as 2 epsilon for some positive epsilon, right? And now you should see the point. Like I want to check that I am delta close for every delta. Well, somebody told me that I am 2 epsilon close for every epsilon. Okay. Formally, it's very formal. Formally, what's quite clear? Pick a delta, write it as 2 epsilon for some epsilon positive, use the property, go back here, and you're done. Okay?
For this proof, though, we only have to prove, we don't have to prove equivalence, right? We just have to prove that 2 epsilon plus
Yeah.
means that you.
Yeah. But the other implication is so trivial that, okay, it's for free. Okay? Okay, good. So, let me give you another little thing. Essentially, we have already proved it. So, if xn has limit, then xn is bounded. In other ways, a way to prove that a sequence has no limit is showing that it is not bounded. Okay? If you want. A way to see that. Having a limit implies that you are bounded. Why so? Let's prove. So having a limit means that, for example, so since n is the limit of xn, this implies that, well, xn in particular, right, is one close to L, at least ultimately. Which is equivalent in saying that there exists a threshold, an epsilon, such that xn minus L is less than 1, right? For every n large enough. Let me call this n0. So for there exists an n naught such that we are one close to L for every n larger than n naught. What does it mean? So this means that xn is less than L plus 1 and is larger than L minus 1 for every n greater or equal than n0, right? I'm just rewriting what I wrote there, being one close to L instead. We are below L plus 1 and then we're above L minus 1. So the modulus of xn will be definitely above the modulus of L plus 1 for every n larger than n naught. So that's a little exercise with absolute values, okay? So that's an exercise with absolute values. That's for every n larger than. So we have proved that there exists a constant such that from a certain point on, the absolute values of all the terms of the sequence is less than that. We gave a name to that, right? What's the name? The sequence is? No, because this doesn't involve every term in the sequence, right? Exactly. So such a sequence we called ultimately bounded, right? So far we have proved. So this shows that xn is ultimately bounded. Alright? Now is there a difference between being ultimately bounded and being bounded? No. There is no difference, right? Because if you are ultimately bounded, you are bounded from a certain point on. What has been left outside? The first n naught minus 1 terms, which is finitely many. So they're naturally bounded. You just take the maximum of their absolute values, that will be the bound. Okay? So we checked that in class last Thursday, and it's in your homework, so I'm not going to write it on the blackboard again. Okay, I did that last Thursday. So, but being ultimately bounded implies, by what we have already seen, that the sequence is bounded. And that's the end of the proof. Alright, so that's easy because, so having a limit tells you that you're ultimately bounded, and then you're bounded. That's easy. Yep.
Didn't you choose one close though? Can you do that without loss of generality?
But I mean, I know that I have a limit, right? So I have epsilon close for every epsilon. If I want to choose 1/2 there, I can. I will just have more. So if you want, that's a very good question. Try to think about this. If instead of putting 1 here, I put 1/2, I get a better bound here, right? Because I got modulus of L plus 1/2, which is smaller. So it's a tighter bound. What could be the difference? That if I use 1/2 here, I'm changing n naught. Typically it's becoming larger, right? Because I'm requiring a stronger condition. Okay? So I can put 1/2 here, but it will hold for less terms of the sequence. Okay, which means that when I complete the step from ultimately bounded to bounded, I have to bound with the maximum of finitely many terms, comparatively more terms, and get a worse bound there. So that's a two-sided bound. You see, I mean, one side of the thing you attack it with the property of being ultimately bounded, the other side with the property of having finitely many terms. You can increase the number of the finitely many terms you want to consider as a bunch of finitely many terms. You can do that. You get a better upper bound there. So it's a trade-off. From this point, from the point of view of this statement, having chosen one, it's immaterial. It's just to say that the sequence is bound. All right? Okay. So let's do. Okay, that's another very easy thing we can prove in one line. So say that you have two sequences and you know that xn is less than yn for every natural number. And you know that L is the limit of xn and that m is the limit of yn. Then L will be less than m. So I have a sequence of, I have two sequences, right? And I know that for each n, xn will be less than yn. So they never cross the other way around, okay? Now these guys converge to L, this guy converged to m, and I want to tell you that then the limit of these guys is less than the limit of these guys. You have already used this thing billions of times, right, in calculus. Now you're going to see the proof. The way it works is by contradiction. You say, well, let's say that thing goes wrong and m is strictly less than m, right? You should be able to tell me the proof now, because write it here, right? So I am assuming that the limit of m of yn is less than the limit of xn. Aha, but that's totally impossible. Why so? Because you open two little windows, right? And now ultimately yn will be here and ultimately xn will be there. Okay, good luck with xn less or equal than yn. Okay, let me write this down. You got the idea? Let me say it once again. So if m is less than L, I can find two little windows such that m plus epsilon is strictly less than L minus epsilon. And once I've done that, xn will be ultimately here, yn will be ultimately there. So for infinitely many terms, xn will be actually larger than yn. End of the story. Contradiction. So let me show you this formally. It will take me 30 seconds. So let's say that m is less than L, set epsilon equal to L minus m over 4. This will be positive. And such that m plus epsilon is strictly less than L minus epsilon. Okay? But by assumption, there exists a threshold such that xn minus L is less than epsilon for every n larger than an epsilon. There exists a second threshold such that yn minus m is less than epsilon for every n larger than m epsilon. So if n is larger than the largest of the two thresholds, then I have both inequalities. In particular, I just need two of the inequalities I have gathered. In particular, yn will be less than m plus epsilon, which is, by the way, strictly less than L minus epsilon, which will be less than xn for every n greater or equal than k epsilon. And this is a contradiction with my assumption that xn was less than yn for every n. This should be all right. I mean, you should be super trained to understand this kind of argument by now. So, just a question for you. Is this assumption really necessary as it written? Does this inequality has to hold for every element? Can you imagine a way of weakening this assumption, still keeping the conclusions? Do you need to know these for the first 50 times of the sequence? You don't care at all, right? You just need this to be true ultimately, right? Because if you know that this is true ultimately, you know that ultimately the opposite thing is going to hold by the other two assumptions. So here it's enough to assume these ultimately. So you don't need the first 5 billions of the sequence to be ordered like that. All that matters is that from a certain point on, they are ordered as you want. And then you infer the conclusion.